Hey folks, this is Dave Nielsen here. The topic is real-time data observability for microservices, a call to arms. Our speaker is Nilesh Dalvi. He's the co-founder and CTO of Layer 9. And before Layer 9, he was the head of trust infrastructure at Airbnb. You may have heard of them. And he was a co-founder of Truly, which was acquired by Airbnb, and was a research scientist at Facebook and Yahoo. So he's put in his time. He got his PhD from the University of Washington and has been actively involved in machine learning and data management. So he's spoken at lots of conferences before. This is not his first time. So I'd like to welcome Nilesh. Nilesh, welcome to the show.
Thank you, Dave. Thanks, Dave and Mahesh. I'm super excited to be here. Monitoring and observability are two things that we are really passionate about at Layer 9. So when Dave and Mahesh reached out to us, we got super excited to come here and present what we're doing. I also have with me my partner Arjun, who I'm not sure if you can see, but we'll tell you about what we're doing at Layer 9 and some of our own experiences looking at working with microservices at our previous companies. Right, so I think let's get started. Now when you think of monitoring microservices, we think of it as a hierarchy of needs, Maslow's hierarchy, where you start by looking at whether your service is available, and once service is up, you start worrying about whether it's kind of returning 200 responses, is it returning errors. Once you see that it's all kind of healthy and returning 200s, then you start worrying about kind of latencies, throughputs. But kind of really the top of that is the ultimate question, which is, is it doing the right thing? And if it's not functional, if it's not doing the right thing, then nothing else matters. It can be blazingly fast and returning all 200s, but none of that matters if it's ultimately not functioning correctly. So that's kind of the zen of monitoring. And today, if you look at APM solutions, monitoring, remediation, we mostly look at the bottom three layers, but the kind of the top layer of this is something that is still kind of out of reach of what we do today. And that's kind of the focus of this talk. So I want to give you some examples to put this into context of what we mean by functional, functional errors. So this is a real world example that I personally dealt with in one of my past lives. Simplified a bit for the talk, but we had a service, a risk service, where you would, for any kind of payment, you would call the service to get like a risk score, and then if it was more than 0.8, you would approve it. I guess maybe that's flipped, but yeah, if the risk was less than 0.8, you would approve it, and then if it's high risk, you would take the user through a verification flow. And the service depended on lots of other ML models and vendors and signals, but eventually one day it started misbehaving and started giving all scores less than 0.2, and a lot of users did not go through verification flow. So eventually, the business metrics on chargebacks were affected and it was detected, but there's often a lag between when a service metric starts changing and when the business metric starts changing, and you really want to detect issues when the service metrics start affecting. So this is an example of what we mean by functional errors, where the service might be up and running and serving 200s, but it's not doing the right thing. Another example is when a service might change its contract and cause issues with a different service. In this example, we have a service A actually returning 500 errors, but the reason is because somewhere way upstream, service B changed its contract. Like maybe it went through some database migration, but one of the fields that used to be a string became an integer. And that actually might be an inadvertent change, or it might actually be a valid change and you didn't realize that that will actually break service A. But in any case, there's a mismatch between service contracts, and irrespective of whether service A is responsible or B, we have a functional breakage. And like this is something that happens pretty frequently when you're running a pretty large microservice and shop and changing your services every time. A third example that looks slightly different is a service that's sending some data externally to a vendor and has some approved kind of contract in terms of what it can send, starts sending something more that might be potentially exposing some sensitive data it should not. And like this was a problem that DevOps team would not kind of think about maybe a few years back, but as DevOps and privacy and security worlds are colliding, in today's kind of DevSecOps world, you do care about whether your service is functioning in a way that is responsible with the data it's kind of logging or sending to external vendors, or just data that it's accessing. So like the three kind of examples I gave, it all kind of relates to services which are doing something functionally incorrect. This was always an issue, but with today's microservices environments and the rate at which it's growing, I mean, this is becoming a pretty critical need as companies scale, as companies adopt microservices, and as they scale the microservices. You're not just growing the number of services. I think the complexity grows in a pretty nonlinear way as you scale your services, where you have hundreds, if not thousands of different entities talking to each other. And in the CI/CD world, you're changing each service every day independently by owners that do not kind of work dependent on other owners. So you're constantly changing each part of your component, and you have all kinds of dependencies between your services. So it's becoming a critical need to understand how services are exchanging data, how they're coupled together, and how does that relate to incidents? How can you detect them? How can you remediate them? If you look at the kind of tools we have available today for monitoring, when it comes to technical monitoring, health, performance, availability, although it's not a solved problem, you still have some good tools, and you can get all the inframetrics, you can get logs, traces. A lot of this can be done without any instrumentation. But when it comes to functional monitoring, it's a wild, it's a kind of a wild land. People rely on ad hoc application metrics. It's a best effort thing. People create ad hoc alerts, but at the end, it's highly incomplete. It's often inconsistent in terms of how you're collecting these kind of metrics. It's often reactive, and an incident happens, realize I should actually be monitoring this aspect of my application, and you add it, and it's highly manual. And given the dependencies of a service with other services, you might be talking to dozens of other services exchanging hundreds of different data items, different kinds of data items, and it's just impossible to manually keep an overview of every single thing that's coming in and out of your service. So the tools today are just not enough to kind of really understand how a service is behaving functionally. So the way we look at it is a service, you can think of it as a black box, a function that has dependencies. So it depends on other microservices. It depends on third-party APIs, data stores. And then you give it some infrastructure, you give it some code, and it exposes some API that you talk to. So really, if you can understand all the dependencies, if you can understand all the data that goes in and out of it, if you can kind of understand how often the infrastructure code changes, you can create a pretty good picture of how the service behaves functionally. And then you can use it to understand when that function changes. You can understand how that depends on other components and how are they changing. And suddenly you can start getting a pretty good picture of, what's normal, what's anomalous, and how you can detect and diagnose issues. So that looks good as a concept, but um, we you know we basically need to add data flows as kind of another pillar to what we do today to monitor. So we have metrics, logs, and traces, but being able to understand data flows themselves, the kind of the you know the magic binding that puts all services together. I think that's kind of the key to understand how services function. So it's easy to say this, but there are lots of technical challenges you need to solve before you can really make it to work. The first challenge obviously is, how do you capture data flows in a way that doesn't require instrumentation, that doesn't require engineers to kind of manually keep track of all the dependencies and instrument them. So how do you really capture all the data that goes in and out of a service? And then once you can capture it, how do you really understand it? What's the semantics of this? How is it changing? I think understanding it requires kind of developing tools and technologies to kind of make sense of the data. So in terms of the first problem, we are seeing pretty exciting advances in kind of technologies around building your microservices stack, and service meshes have become pretty popular. They're coming of age, and as you might know, a service mesh abstracts out all the interactions that your services do. So instead of a service A talking to service B, you delegate that to sidecars that run alongside, and all the interactions between services and data stores and vendors all happens through mesh. So that gives you a very powerful way to capture all the data flows and be able to do something with it. Today, there are a few kind of runaway winners in service meshes. Envoy is a pretty popular choice when it comes to sidecars. So a lot of meshes use Envoy as a way to communicate. So how do you use a service mesh to capture data? Envoy has something called a filter, which is a way to write a custom extension that lets you understand kind of the data flowing through Envoy and be able to do something with it. You can capture HTTP data as well as TCP. And then there's a very recent development around WebAssembly, which is you can write a filter in your language of choice, and then compile it to WebAssembly script and drop into running proxy. So you don't have to pre-compile your filters. You don't have to restart your mesh. You can pretty easily bring in your filters, add it to running mesh, and be able to inspect a lot of traffic flowing through your mesh. And the whole service mesh community is kind of taking this approach of, can we actually look at some of this data communication to understand what services are doing? So Envoy has pre-built filters that come in that understand when something looks like a Kafka traffic or when something looks like a Postgres traffic. So if your application is talking to Kafka servers, you don't have to write metrics to understand kind of your fetch rates and publish rates and latencies. Envoy can understand your communication. It can understand Kafka traffic and be able to understand, what latencies and throughput you're seeing with Kafka. So, there's already a movement from the service mesh community towards adding more and more intelligence in the data communication layer to be able to kind of go back and see what metrics you should care about. But to kind of really go deep and understand how services are functioning, you need to kind of develop a pretty deep understanding of the data flows. And I think it requires kind of layers of technologies. You know, uh, you need to start by understanding what some of these raw payloads look like. People, use a handful of exchange communication formats. I mean, there are REST services that use JSON. People use threads, protocol buffers. There are wire protocols for databases like Kafka, Postgres, MySQL. So now you need to understand when you see some raw data flowing between two services to understand what exactly is it representing. Once you do that, you can start making sense of it. You can discover endpoints within services by just looking at URL patterns, looking at the kind of requests and responses it's serving. And then you can start constructing full API specs. So if you can understand endpoints and requests and responses, you can start understanding how the structure looks like, what are schema elements there. You can then start constructing time series data around how those things change. And then you can understand when service contracts, change, when something is a data anomaly. So I guess you need kind of layers of understanding that turn raw data into something that's telling you something very functional about a microservice. So kind of putting it all together, I describe like a black box view of a service. And to really understand it functionally, three things need to come together. You need to understand the service dependencies to see what are the set of other entities that it's exchanging data with. You need to understand kind of what are the metrics that those data flows represent. And then you need to understand when something external changes in terms of either code or infrastructure. So once you kind of get the three different dimensions in and kind of put them together, you can start drawing a pretty good picture of what a service does, how does it change, and how does it relate to other services. So I wanted to spend some time telling you how this kind of looks in practice. So at Layer 9, we've been looking at some of these concepts and creating some technologies where we can understand services, the dependencies, the metrics, and timelines. And I would love to kind of show you how some of this looks in practice. So we're looking at service meshes, being able to kind of inject ourselves and understand traffic in a mesh. So based on that, we discover services, endpoints, data stores, third-party APIs. It's pretty easy to get your service dependencies based on that and be able to kind of map it and visualize it. A lot of times, when your services kind of become large, just tracking who owns the service, how many of them are running, what team, I think some of that becomes a challenge. So we have kind of turned the service catalog into something that's just a database that you can kind of play around with, change, edit, tag. So you can use it to curate like a list of your services and their metadata like team ownership, service ownership, tag it with in any way you want, so you can kind of search and slice and dice. We are building kind of technologies around understanding data flows to understand not just technical metrics like throughput and latency, but kind of real deep application metrics based on the content of the data, and then kind of using anomaly detection to understand when something looks not normal. And then kind of third dimension to this is timelines, like being able to see when something external changes. So this could be deployments happening to a service. It could be, Kubernetes events around, infrastructure changes. It could be even alerts or issues that your third-party tools report. Just being able to see that chronologically on a time, in a timeline tells you a lot about what's changing. And then as you kind of overlay that with your incident graphs, you can kind of start looking at what events kind of correlate with your incidents and try to see what's the root cause. And often when something changes, when there's an incident, it's not just one metric that changes, but like a whole suite of metrics, start alerting. Understanding kind of service dependencies and correlations can help you group all of the incidents to say, hey, like 50 of my metrics moved, but these all kind of relate to this one core thing because I understand service dependencies and I understand time correlations. So I think with that context, let me actually show you how this kind of looks in action. So this is something that we have put together as like a sandbox running some dummy services. We have about 30 services running. And this is all running using Istio, which is a pretty popular service mesh. So we put some of our technologies in action here to understand kind of the service graph, the service dependencies, and some of the data metrics. So this is giving you a list of all the services. And we have kind of turned that into a catalog where you can tag it with a team. You can kind of assign owners and be able to kind of tag it that you can kind of then use to search. It's showing you kind of an overall health of your stack and what services have issues. You can also look at it as a graph that shows you the service dependencies visually. So this kind of this shows you your service graph, but laid out as a visual graph that shows you the services, the dependencies, and kind of see what the issues are. I wanted to kind of zoom into a couple of services and show you how the data metrics can tell you what's going wrong with these. So this is, let's kind of deep dive into this. So this is a service where we can discover 4 different endpoints. And then we have a bunch of activity feed going on where we're integrated with our CI tools and with Kubernetes and some of the external alerting systems. So it's giving you kind of an activity feed of all the things happening to a service. But it's also saying that one of the endpoints has a data anomaly. So if you kind of zoom into it, we see that this endpoint has a pretty nice structure that we can infer purely based on what's kind of going into the service. So we see that this endpoint actually takes these 7 fields. These are the types, and one of the fields actually is alerting. If you see a time metric for this, you see that the uniqueness count for email, which used to be about 90% unique, has suddenly dropped to 0. So this kind of suggests that maybe all emails are coming out as none or empty. So this is an example of a kind of functional mistake where the service is within its latency bounds. It's giving 200 responses, but one of the fields is just not functionally correct. So you can detect some data anomalies just based on looking at your data traffic. I want to show kind of another example, which is So here's the service. Hold on. But so to show another example where you have a service that is just serving 500 errors. And if I look at this endpoint, I see that I used to get all 200s and suddenly I started seeing 500 errors. So I can actually overlay an event timeline on top of it. So these are showing events that you can get from computer infrastructure, your CI, and any kind of service contract changes you detect. We can kind of rank order these based on correlations. And here it's showing me that the highest correlated event is a contract change, a schema change. If you look at the activity feed, you see there is a schema change activity that shows that one of the dependencies had 2 extra fields, and that correlates with the service actually serving 500 errors. So something that we have taken a lot of log analysis across multiple services become pretty clear when you start looking at data that's kind of flowing through the service. And here it shows you the source of it, which is a traffic service, which is upstream. So I can go here, I can look at the traffic service and I can see who the owner is, or if I have some runbooks, I can go and maybe try to fix the service. So this kind of gives you an idea of how you can start looking at some of the data metrics, data flows, the dependencies, and use that to start looking at when service is functioning correct and how do you can root cause it. So kind of going back to data monitoring, we believe a deep data observability is going to be a pretty critical need as we kind of scale our stacks in terms of its size and complexity. It's as we kind of look at increasing data regulations, increasing kind of complex stacks. This would basically be an essential way to understand how do you kind of monitor and remediate your services. And I think it would require more than just a technology. I think it would require a lot of pluggable frameworks, a lot of service mesh abstractions, open standards, APIs, and a lot of machine learning to kind of really make understand how to look at data. So this is I think at layer 9 we are kind of on a journey towards building some of these, but we hope in the future there will be pretty thriving community that is going to kind of take us deeper towards understanding how services interact. Cool. So that's the end of my talk. Would love to see what kind of your comments are. If any questions.
Great. Thanks a lot. It looks like we have, let's see, what do we have here in the chat?
It's me soliciting comments or questions, Dave.
Okay, great.
But I'll kick us off. I did have one question, Nilesh. How easy is it for somebody to onboard layer 9 to start introspecting their services? And, what's the current model? How does somebody go either get a demo or, spin the wheels, if you will?
Yeah, in fact, I think I skipped over one slide, but that answers that question. So we have basically built our initial technology around Istio, although in theory, any service mesh running, any stack on a service mesh should behave very similarly. So we have currently an integration with Istio where you install Helm chart that brings our filter in, and within minutes out of the box, you start seeing your dependency graphs and all of your data alerts. This all happens with a small sampling. So, it won't increase your network load. It's not going to increase your service latencies because all of this happens asynchronously. And we do all the data processing locally. So we don't want any of this raw data to ever leave our customers' environments. So a lot of this data processing happens on-prem in its own pod. And we have like a SaaS backend that kind of takes all this metrics, and the app I showed you is all powered on based on the SaaS backend that kind of talks to this on-prem component. So I think the power of this comes from being able to do this without any instrumentation. I mean, that's the holy grail, which is how do you understand all of your deep application metrics with absolutely no code change.
Okay. And I see a question in the chat also. It's from Kevin Liu. What do you use for storing the drill down data?
So as I said, we do a lot of on-prem processing to convert a lot of those data flows into time series data. In our backend, we're using our own time kind of abstraction over AWS time stream. But we store time series data, we store contract changes, schemas, and it's all kind of stored as a SaaS offering. And some of it is powered by time stream, some using kind of managed databases. Also, depending on the use case, you can also scrape them directly using Prometheus or some of your own tools. So, if you have your own kind of workflows and monitoring tools, and you're interested in, supplanting them with a lot of pre-rich application metrics, you can also use that as, you can use our on-prem system as just a way to scrape a lot of data metrics that you can put in your own time series if you want.
Well, that's interesting. So some of it is pluggable, sort of?
Yeah, I mean, we think of this as two different components. One is how do you generate metrics and alerts which are kind of beyond the reach of APM tools, which require a lot of custom instrumentation. And the other part is, UI and workflows around it. So if you have pretty mature workflows around it, then you can directly consume the alerts using your PagerDuty or your systems, and you can directly consume the metrics. But we do bring in the power, the dependency graph to kind of really quickly let you root cause. So we believe the UI is a big component of how you really efficiently do root cause, but a lot of these can be used as just pluggable components.
Oh, very cool. With regards to I'm not sure if I got the whole picture on that part where you said you could write for WebAssembly in whatever language you wanted, that WebAssembly supports, and then it would just kind of drop it in, I guess. Where is that actually being deployed to? Like, do you put that into layer 9, or do you put that into something inside the service mesh?
Yeah, so that goes in Envoy. So we have a WebAssembly filter that inspects TCP and HTTP traffic and samples smartly and sends it to our on-prem agent. All of that runs within Envoy. So if you're running Istio, you are most likely running Envoy, and you might be running a different service mesh using Envoy. So our filter sits in Envoy, and that's our only requirement today. But in principle, something similar can be done for other service meshes as well.
Yeah, interesting. Okay. And are you guys specifically requiring Envoy for your service?
So currently our first offering is for Envoy. And we are kind of running this in production with a few of our customers who run Istio in production. But yeah, would love to look at other ways we can plug into other kind of stacks and service meshes. But yeah, today our offering is for kind of any mesh running Envoy.
And how do you relate this to, oh, actually, here we got a question in here, I think. Let me check. Okay, here's a question from Kevin. He asked the previous question as well about storage. He says, as a customer, do I need to specify the schema or requests so that layer 9 can analyze each field of the request?
No, so I think that's the real power, right? So now we don't want engineers or developers to manually specify what the endpoints are or what the schemas are, because I think that's always the source of, kind of catching up with how you change things. So anything that requires manual input or integration always lags behind what happens in practice, in production. So everything happens for us out of the box. As I was describing, starting with raw payloads, we're able to kind of reconstruct semantically, what the structure is, what the schema elements are, what does the API spec look for an endpoint, and then create time series metrics out of it. So all of that happens purely by inspecting data packets. We don't require any kind of manual input towards this.
So I suppose that's sort of where the data observability part kicks in, right? Like is that why you call this data observability?
Exactly. So looking at how services interact, right? Like people say microservices are basically a way to decouple your logic, but in reality, all of your services are very tightly coupled because they exchange data, and you require very tight service contracts between services. So that's the kind of data observability, is understanding what the service contracts are, what are services exchanging, and how does that change?
Right, I can see that. Okay, let's see. All right, folks. So if you have any other questions, please chime in. And then how would you relate this to, let's say, the standard distributed tracing frameworks that are out there, like started off with Zipkin and then Jaeger, and now there was the Open Tracing and Open Census, and now we got Open Telemetry.
Yep.
How do you see yourself fitting in with that?
So I think traces are definitely a big, it's an important pillar in any monitoring solution, and it's kind of in parallel with the data pillar. Like traces would tell you how your errors and latencies are distributed in a kind of a deep microservice call. So traces will tell you if your eventual request took 100 milliseconds, how does that kind of translate in terms of all the intermediate calls you made and the dependencies. Think of this as kind of tracing for data, that where we are looking at how does a data dependency change across your service call stack. So if a service is serving an error, we look at what changes in its input and then trace it all the way back to what might have caused, which service might have caused it. So I think it's looking at different aspects. Open tracing, open telemetry would look at how latencies propagate through service calls, and we look at how data propagates.
Okay. Got it. Okay, interesting. Very good. All right. So I think at this point we can wrap up the Q&A. And if anybody has any questions while we're going through the raffle, feel free to chime in.
Well, I mean, we'll love to, hear your feedback. So if you have any comments, please do reach out. We're always interested in understanding how people do their monitoring, what lessons they have learned from it. So, we'd love to chat about this if you have any comments.
Great. Okay, thank you, Nilesh. All right, yeah, great. Thanks, Kevin. All right, so Kevin says, great presentation, thank you.